Hi. Let's start with the chart. This is what a measles epidemic looks like. This is a chart from Israel, although most of the world is now suffering from that. And as you can see, this chart of this spike and then going down, this is about 4,000 measles cases in Israel around between 2018 and 2019. And just that you believe it's actually an epidemic and an outbreak, well, this is how it looked like 10 years before. So we had 4,000 cases in around, and the 10 years before that didn't have like even 1,000. So this is an outbreak, and that's a problem. And as you can see also in Europe, specifically in Poland, this happens. Like measles is now around the world. But yet, those cases are like a fraction of what we used to have 30 years ago, 50 years ago. So we ask ourselves the question, what changed? And the answer is vaccines. And is it that simple? Well, yes. But actually, no. So giving a vaccine to one person, that's easy. But vaccinating an entire population, that's pretty hard, because you have to ask yourself some questions like, on which ages do we give the people the vaccines? How many? Because some is not enough. Like if you give, on measles, you need at least four vaccines when a child is born, but not immediately when they're born, just after 1 year. So some is not enough, but then maybe some is too much. And for that, we need disease modeling. So this talk is disease modeling with Scipy and PyMC. This is me, my first time speaking not in my country, Israel. So thank you for welcoming me here. My grandfather was born in Poland, so this is kind of a nice place to have the first time. I work in Sentinel-1. It's a cybersecurity company in Israel. This is not related to what I'm going to talk about. I'm also volunteering in an organization called Data Hack, which is a non-profit for the advancement of data in Israel. And my talk is about disease modeling, which was my master's thesis in the university. I also built a website called Epidemic COIL, which shows you how different diseases progress in Israel. And let's start. This talk is going to have 6 parts. I'm going to show you what's a dynamic model, because a disease model is a specific kind of a dynamic model. So the second part will be disease models. Then I'm going to learn a bit about MCMC. Maybe we'll skip that in a rush because I'm not sure we have enough time. Then we're going to see how we take the model that we've built and use the MCMC to fit it to data that we already have from the Israeli Ministry of Health. Then I'll show you why we need it, because we need it in order to simulate future possibilities and realizations of the futures, in order to understand different policies, what's the effect of different policies in the future. Then, because you're going to see some toy examples, it's not going to be that interesting. I'm going to show you the results of like real research using those methods. Let's start with the dynamic model. Who's done dynamic models, and specifically in Python? One person. Cool. So a dynamic model is basically what you see up top. You have some groups in the population, and they interact with each other. So let's say kids, they become adults, adults become mature. The mature people can die, the kids can be born, and the adults can make new kids. So those arrows actually define how the system behaves. And specifically, let's say, you can say, now you're going to try and see. So you look at the system over time, and you can say maybe the kids at time point 7, let's say a time point is 1 year. The kids at time point 7 is how many adults you have in the population. Time that with the average kids per person, and but don't forget that some of them get they get adult, they age, so they get into the adult group. So you can say that the kids at time 7, and that's a function of adults and kids at time 6. And basically, you need to start with like the state 0. So you say that I invented that some of them, like 100, 800, and 100 kids, adults, matures. So that's what we call state 0. Then you have the rates, like when a child becomes adult. So you say in age 21. So every year, 1 divided by 21 people become adult, and so on and so forth. So we have the rates, and now all you need to do is a Python loop. you take each time point out of, let's say, for 80 years, and you say, well, this time point is a function of the time points before then. And basically now you have vectors, and you can try and graph those vectors, and you can see that so on the top part, you have the sum. So you see that more people are being born than they die, so all the groups go up. And on the bottom chart, you can see like the normalization of that. So you can see that there are more kids and more mature people as we progress, and eventually it goes into what we call a steady state. And this is how the population looks like if nothing changed. So what's a disease model? A disease model is basically a type of a dynamic model. But instead of talking about ages, we're talking about disease progression. So some people can be susceptible to the disease. That means that they are not currently sick, but they could become sick because they haven't yet. Then if they got infected, they become into the infected group. And once they recover, they go into the recovered group. And on the most basic model, that's the most basic model of disease modeling. After you become recovered, let's say in chickenpox, you can't go sick again. That's a nice disease to have. And also you have now the state 0, and now you have the recovery rate. You have all the rates. One of them would be the recovery rate. So that's easy. We can see about a disease, we can say how long does it take to recover from it. So that's an easy rate to have. And then you have beta, which is the force of infection. So this says, if I'm meeting an infected person, how easy it is for me to get infected. And each vaccine has their own unique beta. But what is this beta? So this is now our little secret. This is a magic number called force of infection. What you're gonna do is later we're gonna see what beta is. That's what we're gonna fit to the data and get the distributions of beta. And basically you have the same. Now instead of talking about discrete time points, let's say those are derivatives. So the derivative of s at time t is some function of s and I and r. And instead of using a loop to solve that, we're gonna have the state 0 and the rates. But instead of having a loop to solve that, we're defining the function as a function that receives time points and the vectors that we're interested in. And then we use Scipy to solve that. So that basically it's a differential equation model, and Scipy solves that for us. What Scipy is going to give us? So you see that sol is the function solve, and what Scipy is going to give us is this object that one of it is the vectors of the solutions. So this is not very interesting. What's interesting is when we chart that and you can see the disease. So now that's the pretty interesting part. You can see that disease, if you looked closely, started with like 1 person sick out of 10 million, but the disease was pretty strong, so we infected people very quickly. So the sick people are the red line. Many of them got sick very fast. Then most of the population were already sick and recovered, and we said that you can't get sick again. So again, it went down very fast, and now most of the population was sick at some point in history, but now the population is pretty healthy. So that was a nice disease. A worse disease would be that if you recover, you're immune for the disease for a bit, but then you can become sick again. And then we can write again the model. So again, we define some parts, and then we define the function. Just instead of not returning this, we have the minus gamma r. So the gamma r is the rate in which we become susceptible again. And then we solve that, and we can plot that, and now we can see that the disease is not going down to 0. It's still not very strong because it's not an epidemic, but it's still lower than the susceptibles and the recovered. But you can see that at each time point, so it basically becomes a steady state where at each time point, about 0.5% of the population is sick in this specific disease. In Israel, it means that at each time point, about 30,000 people are sick at, let's say, the flu or stuff like that. In Poland, it would mean ×5 that because the population ratio. So imagine 150,000 people have the flu at each time that you're looking at. So what's MCMC? You can now take all the two parts before then, keep them in mind, but you're not going to need it for this part. MCMC is a method that we have in order to find distributions of parameters. So basically, it relies on the Bayesian formula. This is what's called Bayesian. This is one of the ways to fit Bayesian models into data. So basically, we want to ask ourselves, let's start with an easy example that would be a linear model, right? We want to ask ourselves, those points, I can tell you that I simulated them, so they come from, I think, 3x plus 4. But we're going to ask, what's the chance that they come from 2x plus 5, right? So given the data, I think A is 2, B is 5. What's the probability of that? Well, we don't know that. What we do know is that if the model was in fact that, what's the chance that we got the data? So we flip that using the Bayesian formula. The thing is, we need now two other things. What's the probability of A equals 2 and B equals 5 somewhere in the universe? And what's the probability of the data? Two terms that I'm not actually, you don't even have the words to understand what they actually mean. The thing is, we're not going to need them eventually. What we're gonna do is that now what we have two competing offers, we can say which one of them is more likely. Now that's nice because the P of the data, well, that cancels each other out. And also the second part, this is actually mathematically not canceling each other out. For this talk, let's say they do cancel each other out. This part will always be the same. So what we're left here is what's the probability of the data given one model, and what's the probability of data given a second model. And in this specific point, we can say that the left part is larger. So now, always remember, we have two different competing options. One of them is better. If it's better, great. Let's look for another one that's maybe even better. If it's worse than now our candidate offer, well, let's skip it, but not like skip it all the way. Maybe on some events, maybe also try it and explore the space. So basically what we're doing MCMC, we're exploring the space giving this formula, and eventually we can see that we're exploring the space and we get options for A and B, and you can see that the simulated offer was 3x plus 4, so the model found that. This was the most highest density of the searching the parameter space, but we can also see a distribution. So now you're going to ask yourself, well, we know linear models, why not just find the 2 points? And it's probably correct for linear models, but this is a good example for learning. What you can see now is that you have a parameter space that how like A and B are acting together. And this is the solution that the model finds, so it's pretty much close. So this is how it was defined. And this is how you do it in PyMC. You define two parameters up top. Then you only tell the package, you tell PyMC, well, y hat is how we define, is basically a linear model of A and B. Then you tell PyMC, well, now sample, search the space, basically. And this is going to do it for us. It's going to take a little bit of time because it's now sampling the space. And it's going to return us a result, right? Because we have now a distribution. So those are the marginal distributions of A and B. And it says, well, I'm to 4. Sorry, A is close to 3 and B is close to 4. And well, this drawing gives us also the sigma, like the variation of the data, and from simulating it, I can tell you also that this is close, so yes, great success. The beautiful thing about Bayesian modeling is now that you told me, right, 2 minutes ago, you told me we don't need it for a linear model, and I'll tell you that's correct, but once you have a bit more of a complex model, instead of starting to look for like different models that try and predict like a cosine function or maybe something with many like powers and stuff like that. You can just tell, you can do everything you've done the same. You define a PyMC model and then you just tell it, well, the formula y hat is not ax plus b, it's ax plus b and a cosine of something, and then you just tell it, well, sample this and give me the results, and then when you sample this, you get the sigma and you get the parameters, and you can see that it's pretty close to what we simulated before then. You can also do an outlier removal. So the way we did the linear model, we tried to predict it. We said that the error is normal. So now let's tell it the error is it's not from the normal distribution. It's from a student t-test distribution. And if you know that it's more forgiving for mistakes, let's call it. Again, not mathematically official, but it's not bad. So then you can see that the model, when you're trying, if you have an outlier here, like up top, and you give it the normal distributions, it gives you a bad result. But if you're trying to predict it with the student t distribution, well, now you can see that the yellow line, which came from the student t simulation, is a lot closer to the simulated line. So again, we only changed like one line of code, and now it predicts it beautifully. And that's it. That's basically MCMC. It is searching the space with some probabilities, and eventually gives you distributions of parameters. Let's talk about model fit. So now you have data. Specifically, we had data from the Israeli Ministry of Health. And it looks like that. And we want to predict that. Well, we can try and predict some model that comes from a formula, but we want to do something more. We actually have a disease model. So what I showed you earlier, when you go into real life, basically the models are more complex and they look something like this. You have the susceptible population, but also you can choose maybe vaccinate, maybe not. If you do, on which ages, stuff like that. And then you have the rates. The parameters are what basically are the rates were before then. And you define the model. We did that part. The only things that we don't know, and I told you, well, this is our little secret, is that we have some magical number that is called the force of infection that basically says how infectious is the disease, right? Everything else we got from clinical trials. But now we have a tool to solve that, right? We have the MCMC part. So if we have data and we have MCMC, let's just take the model. Well, let's define all the parameters that we don't know. One of them would be, the only one would be beta. Now let's say that y hat, instead of being a linear model or some formula, it's a black box that tells us this is how the disease looks like. And then we can simulate it the way we did this before. But you also know how the black box looks like, and the black box is a disease model in the shape of different differential equations that are solved with Scipy. So you know everything in that part. You have the data, you have the MCMC, you have the Scipy. Now you just need to actually run it. And MCMC tells you, well, the beta is, the modal point would be 1.42, but then it's coming from this distribution. So great, we actually predicted what we wanted to predict, and we can look in the disease and see, well, this is close to the data. But you ask yourself, why? Why do I need this beta? Give me predictions. And what I'm going to say is that this type of work is not trying to predict. I'm not trying to predict if the amount of sick people in 10 years is going to be 1,000 or 2,000. Those models are not good for that. What I do try to predict is if I'm going to tell you vaccinate children instead of at the age of 2, vaccinate them at the age of 3, which one of them is going to have less sick people in the entire population. So we have the beta. In order to do that, we need to actually simulate the future possibilities. We have to simulate one option with vaccinating kids at 2, one option with with vaccinating kids at 3. And this is the simulation part. So when we have a simulation, we actually need to search the space, but we're searching a space that is not known. But for this, we have the distribution of the beta. So we can ask ourselves 2 competing models. One of them, like we had a disease, we ran the disease for a few years, we got the distributions of beta, and now if t, like after 30 years, so if t is larger than 30 times 52 weeks, then p becomes new p. The thing is, what's the new p? So I have 2 options where new p could be 1 and new p could be like 0.5. And then I can run the model, right? Because here we define the model that runs and returns a result. And for each possibility, we have now the solutions from Scipy, which returns a vector, and we can plot that vector. And you can see that the red option would be with the new p. So a p is, sorry, I didn't say what p is. A p is trying to understand how many people actually vaccinate. So P was 0 because nobody was vaccinating in the first 30 years. And then we ask ourselves, what's the option of people vaccinating at the age of, like all the population, 100% of the population are vaccinating. And what happens in the option that half of the population is vaccinating. So that's basically P. And you can see that if the entire population is vaccinating, the amount of sick people is a lot less. That's the green one. That would be a lot less than the red line where half of the population only vaccinates. So that was a simple example, and you can see that maybe after knowing a lot of dynamic models, you can see that, well, that's not surprising. If you have less people vaccinating, it means more sick people. So the more interesting examples would be what happens when we do have a real disease. So in my master's thesis, this was the real model. So we had a model that looked like this, but also it had age groups. So imagine that we have those 6 compartments, and we can ask at each point, we can say, well, if the year is more than 57, we got this type of vaccine. But then after 2002, they changed the vaccine to a different type of vaccine. What happens when you change the vaccine type? And then you can become 2 types of infected. Some people feel the disease and actually they stay at home. So they have a strong disease, but they stay at home. And some people get a little bit of the bacteria, but they don't feel it, so they go to work. So they could be more infectious because they actually meet people. So what's more infectious? Well, that depends on on other sociological factors. And so we have all the parameters, but still we don't know beta. The thing is, beta is not a scalar anymore. It's like a vector, because at each age also the disease could behave differently for different people. So beta is not just one number. It's like the amount of age groups that we have. And also we're gonna ask ourselves, like, if I'm 30, what's the chance of me meeting a person that's also 30? Or what's the chance of me meeting a person that's 20? And this matrix says that. So you can see that kids meet each other a lot, but they also meet people that are like 25, 30, because that's probably their parents. But you can see that basically we meet people our own age, so we infect people that are our own age. And this force of infection thing, it's no longer a number, it's not longer a vector, it's basically a function that says, how am I infecting depending on who I meet? What time of year is this? Because maybe the bacteria itself behaves differently in winter or in summer. And that's basically become now, instead of one number that we need to predict using MCMC, we're trying to predict about 7 numbers. And those are some results. So the red ones are actual data from Israel of people being sick in a specific disease that's called pertussis. And the prediction that we had, like the fit that we got from the MCMC, is the black line with more realizations of the simulation in the gray lines, and then we can ask ourselves, we simulated different futures, and what we asked ourselves was, let's change the age of the vaccines. So now the kids are getting a vaccine at the age 5 and at the age of 7. So at the left part, you can say, we're going to ask ourselves, what happens if we vaccinate them instead that on 13 and 18, or at 6 and 10? And the more left you go, those are less sick people, and the more right you go, those are more. So on the red parts, you can say if we take one vaccine off. Maybe we don't need that. Maybe we can vaccinate the kids only at the age of 7. You can see that we have a lot more people sick. In the blue parts, you can say just take the 2 and change the ages. And on the yellow part, you ask yourself if we had another vaccine. So you can say that if we had another vaccine, well, that's simple. We're going to have a lot less sick people. But then other questions come to mind, like, do we have the money for that? If we can use the money for vaccinating against the flu or measles, maybe that's better. So we stick with let's keep all those vaccines. Let's keep the 2 vaccines. Let's just see if we can change the ages. And we can see that instead of vaccinating kids at 5 and 7, we said that if we vaccinate them on instead of 5 and 13, we vaccinate them. Instead of vaccinating them on 7 and 13, we say let's vaccinate them on 5 and 13, and those were the best results. Sadly, they were not good enough in order for the entire system to change its course. We got the results that we're going to have 1% reduction in the disease, but then it would cost a lot of money, and the entire system going to need to be changed because we take one vaccine, and instead of vaccinating kids at school, they're going to do this in the kindergartens. So many other different problems that we can't answer with Python. So in my specific case, it didn't become a policy, but that's how you do. You look for policies in PyMC and Scipy. Remember that all models are wrong, but some are useful. And in this specific case, it's actually correct, because again, we're not trying to predict how many sick people, just what different policies are going to do in order to, like, how they're going to behave next to each other, which is the best policy. This is me. You're welcome to my website, my Facebook, my GitHub. Specifically, Dove Panda is a new open source package that I'm welcoming you to try. It's going to help you write better pandas code. Thank you.
Thank you. We have a time for one question, maybe 2. Oh, there's one on the back.
Hi, thank you for the talk. I was just curious for PyMC, which I haven't used a great deal, but the way you set it up, I mean, you had a prior, essentially a linear model. Is it easy in this package to set up multiple priors and then search through multiple parameters for different priors, and maybe have, in terms of speed, maybe have some sort of parallelization framework in place? Is that supported?
So again, you heard like 2 questions. So is it easy to parallelize it?
Yeah. So right now in your models, you assumed you had a sinusoidal function in one, and another you had a linear function, and you searched over the parameter space. But let's say I don't know what the prior is. Let's say I have no idea for a particular data set, and I want to explore a large universe of priors and see which one fits. Is that possible? I mean, of course you could set it up manually, but is there support in PyMC for sort of automating this process?
So what I had was, so I understand the questions. I'm not sure, because what I used is defining the basic priors. Like, let's say A behaves like its distribution is its prior is normal, and then this is the model, something with a sinus. I'm not sure if it can actually look for different models. I believe no, but maybe I'm wrong. Because the entire part that you do in the disease modeling is actually looking for what's the best model, but in disease modeling, a model is not a formula again, so this is the hard part, actually trying to fit a model into the reality. So I'm not sure how it's going to look for different models, but maybe with easier models that are like can be formulated into one formula, maybe it could. I'm not sure.
Thank you.
Thank you so much. Great applause, please.